Okay, so in the last video we were looking at U substitution to solve integrals, and I just wanted to do a few more integrals and examples here so you can kind of get a good idea of all the different ways we use U substitution. So suppose we have this, the integral of sine x cos x dx. And now that looks like a product, but we said in the last video kind of try to visualize these not as a product but more as a composition of functions. And in this case, I'm going to let u be sine x, then du, the derivative of sine, is cos x dx. And now if I do my substitution, this becomes the integral. Sine x is u, cos x dx is du. And now this somewhat complicated looking integral is actually really trivial. And this becomes u squared over 2 plus c. And then of course I substitute back and I get u, which is sine squared of x over 2 plus c. And then maybe we have something like this. The integral of ln of x over x dx. And now I'll point out, we don't actually have any way that I'm aware of to integrate ln of x. There are tricks that we'll learn later on, but for right now there's no trick we know to integrate ln. We can differentiate it. The derivative of ln is 1 over x, but we can't integrate it and go backwards. But since I can't integrate that, I'm going to let u equal ln of x. And then du equals the derivative of ln, which is 1 over x dx. And now we see this becomes the integral. Ln of x is u. 1 over x dx, 1 over x dx is du. And now that I can integrate. Antiderivative of u is u squared over 2 plus c. U is ln of x, so this is ln of x squared over 2 plus c. One thing I would point out as far as this goes is keep in mind, this is not ln of x squared, where you could then bring the 2 down. This is ln of x squared, so you can't bring this 2 down and cancel. If you could, and you did, this 2 would cancel with that 2. This would just be ln of x, whose derivative is not ln of x over x. This is ln of x inside of a square. So you would chain rule it, bring down the 2, ln would stay the same, then take the derivative and all that. So just keep that in mind. You can't bring down the 2 here. This is not ln of x squared, it's ln of x squared. Okay, good. The other thing I wanted to go over, so far we've only looked at indefinite integrals with u substitution. We want to do definite ones too, but it's pretty straightforward. Suppose I have the integral from 1 to 2 of, we'll just go with x times x squared minus 2 squared dx. So we say, okay, I'm going to do u substitution here. The inside of the parentheses will be my u. So u is x squared minus 2. Du is 2x dx. If I then substitute back here, this becomes the integral. X squared minus 2 is u squared. I need x dx. This is x dx. So I'm going to divide by 2. And now x dx is du over 2. So du over 2. Now there's one problem here mathematically, and it's how you choose to see it. These limits of integration are limits of integration with respect to x. This integral is now with respect to u, which means those limits of integration don't work anymore, because this is a different variable. There's 2 ways you can go here. I'm going to show you both ways. Ultimately, I don't care which way you go to solve the problem. as long as you can solve the problem. The first thing you can do is, don't worry about the limits of integration now, integrate like normal. So if I integrate, the 1/2 carries along, I'll raise the power and divide by 3, so I'll get u cubed over 6. Now, substitute back, I'm going to shift this over. I get u cubed over 6, raise the power to 3, divide by the 3, which is, my u is x squared minus 2, so that's x squared minus 2 cubed over 6. Now, I've substituted back for x, now I can plug in my limits. So I'll evaluate from 2 to 1, and I'll get, if I plug in 2 squared is 4 minus 2 is 2 cubed is 8, that's 8 over 6, minus, if I plug in 1 squared is 1 minus 2 is negative 1, negative 1 cubed is negative 1 over 6 is negative 1/6. So 8/6 minus negative becomes plus 1/6, and we get 9/6, which is 3/2. Okay, there is an alternative way to do this, and what we do is, right here, I have the integral of u squared over 2 du. I say I need to replace these limits with limits for u. If I want to do that, I just go right here to my substitution. Plug in my limits for x here to find associated limits for u. So, if x is equal to 1, u is 1 squared minus 2. 1 squared is 1, 1 minus 2 is negative 1, so my lower limit is negative 1. If x is equal to 2, u is 2 squared 4 minus 2, which is 2. Now I have limits for u, now solve that. So if I integrate, I get u cubed over 6. Now since these are limits with respect to u, I can just evaluate there. If I plug in 2 cubed is 8, so that's 8 over 6, minus if I plug in 1, negative 1. Negative 1 cubed is negative 1 over 6, that's negative 1/6. 8/6 minus negative 1/6 becomes plus 1/6, and we get 9/6, which is 3/2. And the point is, it doesn't actually matter which way you do this. Personally, I generally do it this way, and I'll do my integration with respect to u, substitute back, and then plug in your limits. I just prefer that for whatever reason. I think that's the way I did it when I was in school most of the time, so I just kind of stick with it. But you can just as easily change your limits. We'll do one more of these just so we can see it worked out. So suppose we have the integral from 1 to 5, we'll go with 1 to 3, doesn't really matter. X e to the x squared dx. We've already integrated one like this before, but we care more about the limits here. So we know I'm going to do u substitution. So I'll let u equal the power x squared, du equals 2x dx, and now since I kind of know what I'm doing, I know ultimately I'm going to need x dx, so I'm going to divide the two right now. Now I have my x dx. Now, I'll substitute back and I'll solve the problem both ways. Here, if I keep my limits with respect to x, it's the integral of e to the x squared, which is e to the u. X dx is du over 2. If I integrate, the 1/2 carries along, and the antiderivative of e to the u is e to the u. Now I substitute back in. U is x squared, so that's e to the x squared. Now I plug in my limits from 3 to 1. I get 1/2. That'll just carry along, so I'll pull it out. If I plug in 3, I get e to the 3 squared, which is 9, minus e to the 1 squared, which is 1. And I know I can just write that as e. I'm just writing it as e to the 1, so it's explicitly clear. And now I have that. And I'm just going to leave it like that over here. if I integrate e to the u over 2 du, and now let's see. If I plug in 1 right here, u is equal to 1 squared, which is 1. If I plug in 3, u is equal to 3 squared, which is 9. Now I anti-differentiate, the 1/2 carries along, and I get e to the u, evaluated from 9 to 1. And that's 1/2 e to the 9 minus e to the 1, which is exactly what I got here. And again, the point being, it doesn't matter which way you actually do it, you'll get the same answer as long as you do this substitution correctly. Take these values of x and plug them into your substitution to get the associated limits for u. And again, as always, if you get concerned that you're somehow doing it incorrectly, do it both ways. Check yourself.